I'll show you the same handwritten piece of paper I have in front of me. Accidentally, but it turns out to be a moral tale about this course. So I will show it again and show it again. So this happens to be what I'm doing for a living for a very long time. And, you know, science is hard enough that even such a thing is simple enough. So what I do for a living right now is called turbulence, and sometimes it's called quantum field theory. Sometimes it's called other things. But, you know, basically the reason why I think it's good for everybody to take this course is that if you do real research, you will invariably have to deal with nonlinear systems. Even things that pretend to be linear, like quantum mechanics, are not linear. It's a science which is relatively new for, you know, it could have been done in 1880s were it not for the fact that it was extremely tedious to do calculations of necessary kind. It could have been done then. It doesn't require quantum mechanics. It doesn't require special or general relativity. You know, it doesn't require the great things of 20th century. But it actually helps to learn them because interesting insights have been obtained in the nature of reality and this description that enlightened this very classical problem. Now, classical problem is how do you compute? In 1880s, 1890s, there was a professor in Oslo who read Henri Poincaré, the great French mathematician's idea about how celestial mechanics works. He wanted to understand the polar light, aurora borealis, because if you're Norwegian, you see amazing, beautiful aurora borealis in the winters. And equations are known. They're charged particles moving in electromagnetic fields. So it's not a big deal to do this. So my professor, having read papers by Henri Poincaré, which are papers without single picture, but rich in deep ideas, learned the thing that he should understand the trajectories of charged particles in plasmas. And their radiation is what we see as the polar light. And he set out to compute this. And not only did he set out to compute it, but he made a number of what was called amanuenses and what we call graduate students to it. Amanuensis is a guy who helps you with your hand. They were all men in those days. So amanuensis, you pay some miserable wage, so he's allowed to hang around Oslo University. And he set them to solve by hand ordinary differential equations of charged particle moving in plasma. Equations are beautiful, simple, precise. This happens in 3 dimensions. And I had a handwritten picture of what his opus, he and his slaves, the graduate students, did over his tenure. But basically, it looks like a piece of wire. So it starts, you know, and then it twirls around and then goes like that. And that was the longest Poincaré kind of conceptual trajectory ever computed before roughly Second World War or years after Second World War, when mathematicians and physicists and engineers were allowed to return back to science and not just killing other people. So Lady Cartwright, one of the founders of theory of chaos, computed similar trajectories in a simple simpler system which had to do with vacuum tubes, which had to do with radars rather than with plasma. And today, after you hear this lecture, you can solve the professor somebody's problem from Oslo in a day or two, because you have to learn how to use MATLAB or something, and you have to learn how to put an equation in, and then you have to learn how to look at graphic output. And those trajectories, an undergraduate should be able to compute. If it's an incredible undergraduate who shouldn't be an undergraduate in half a day, or if it's a credible one as a project in this term semester, for example. So what has happened is that the tedium of computation was relieved by quantum physicists. First, it was done by computers. So the wartime computation were done by girlfriends and wives of male physicists who were creating atom bomb in Los Alamos, and their partners were the farms of so-called computers, which were women doing hand calculation needed to design atomic weapons. By the end of the war, the tube calculators, so like radios or televisions with tubes, with lots of tubes, dissipating an enormous amount of heat, were already coming in. By the 1950s, mathematician von Neumann had a machine at Princeton, and various machines existed called Maniacs, etc., which filled large rooms. By the mid-60s and 70s, it was possible for a graduate student or professor at MIT, in this case, Professor Lorenz in meteorology, to get an analog machine, their hands on an incredibly expensive analog machine or a digital computer machine to do calculations. And now your phone is much more powerful than any of those things, but it's a stupid phone, so it's impossible to do anything useful with it except spread misinformation. But in principle, you could program this thing to do and design what was needed to design a nuclear weapon. So the situation is totally changed, and we can do 19th century calculations. So we can even do turbulence calculation, the thing that's supposed to be indicated by my little humble drawing here. Now, I can't help, to hector you, to tell you that there is no replacement for thinking. There will be no replacement for thinking. We will have to have machine learning. We will not be able to progress in many branches of biology, neuroscience, astrophysics, physics, etc., without machine learning. And it'll be totally essential to understand what these things are doing. So instead of boring you with moral stories of people who have done good calculation, how they've done it, I'll give you some links on the home pages, because it's a great temptation to go on a big tangent. I'll just start discussing, I'll return to this picture a few times, basic idea of how numerical computation works together. So here is idea number one, is that if you have a semi-decent education, you've encountered some ordinary differential equations, thanks to Leibniz and to Newton. And you have to solve them. And applied math is a branch of mathematics where people actually do this for a living. But physicists have to do it as well. So here is a typical one. Now, today I will use letter X just to tell you it's more general, but whenever you find X confusing, this is really going to be time, because in this subject we'll start by thinking as though this is late 18th century and there is absolute space and absolute time that Newton believed he lived in. So second derivative of my position, meaning, end of a spring or a mass hanging on something, with respect of time, is called acceleration. First derivative is called time. So lots of problems, lots of good physics problems have this form. This even has a name, which I won't tell you, but you will learn it and go to applied, mathematical methods course. You have to look at second derivative of whatever you're observing, like position of the end of a spring in very simple examples as a function of time. So this y is something that you're observing. And in general, what happens to this depends maybe on the first derivative. This is called friction if you encounter first derivatives. If you have symmetries, like you want your law not to know what's the difference between future and the past, you will not be allowed to have odd derivatives, but in general you can. If you forbid this, you get Hamiltonian mechanics and celestial mechanics. If you keep it, you're studying, swimming of a little thing in a fluid, little spirochete. And it might depend at the time, so you might have some friction, you turn on and turn off, so there might be something here, some law. And to make this thing go, you have to force it. So there is some law. And usually this has meaning. So this is an acceleration. This is forcing. And this is some kind of friction. Maybe variable, I turn it off, I turn it on. I heat up the fluid, I freeze the fluid, so it's honey, so it's fluid and not fluid, it's gooey. And just to keep you on your toes, we will say that there is some variable x, which between you and me is actually time. But if you're applied mathematician, or if you're a condensed matter physicist looking at a lattice, it might be really position in a space of your atoms in a lattice. So it's okay to think of it abstractly. And now one says this equation is second order. Because it has a second derivative here. Now, in this course, we'll do something that seems innocent to you, but it's actually often criminal. I'm sorry I'm using this term so lightly in a world full of real criminals, but here we are. It's let's say that it's insensitive. It seems to be a good idea until you learn the subject deeply and you realize it's a very wrong idea. But the usual thing is to say, let me just say that first derivative is some function. And then when I take the first derivative of that function, I get this thing here. So that equals r of x minus q of x. C of x. This is this thing. So this is the same equation. We just wrote it in terms of 2. And in general, This is a prescription that anything you want to do, you can do it as a set of first order equation. And if you understand how to solve those, you might understand how to solve those as well, right? So the setup for this course, entire course in nonlinear dynamics and chaos, where this becomes a really, really bad idea, is to say that I'm looking at the systems which can be written as first order differential equations. And that means I have a state space, which is space of possible values of function y and function z. Because I have equation for two of them, I call them y1 and y2. So there is an index here. So I have a set of equations. And what it means, first order derivative, this is really time. So these stupid f's functions, they're really meant to be velocities in this abstract state space or phase space. So the way you think of it, you have some kind of volume, it has some number of dimensions, each for one of these guys. So it depends on time, sometimes explicitly and sometimes implicitly. And then it depends on where I am in that state space, which is, capital N numbers, where index y is as many equations I have. First one I'll call 0, easy to drop to n minus 1. So this is what a book like the one that we are studying right now, we call dynamical systems. It has the state space. So these are all possible values of these states. And then it has the law, and the law is that, so we call this a manifold in general, but right now it looks very Cartesian. But when you look what's really allowed, it's some curved thing because there's some constraints typically. And the law says every one of these guys, so there is a vector of these guys, is velocity that depends on it, where these guys are d-dimensional vectors, n-dimensional vectors. So it's a little bit of abstraction, but it removes you from your immediate intuition because, it's the kind of thing that you would learn in mechanics course if Georgia Tech was still requiring mechanics courses, but apparently we don't need to teach that anymore. That you need to know for Newtonian physics, at least position and velocity of every particle. And that combination of the two spaces is what's now called state space or phase space in this book. Now, this is a small subset of how dynamical systems work, because very often it's convenient, as you will see pretty soon, to look if it's a repetitive, boring thing, so some system that's being, for example, in the basement of our building, people are very good in having, 100 atoms at super cool, sitting in some very soft parabolic potential, and then they shine laser light on them of a given frequency, and as far as atoms are concerned, they're sitting on some kind of washboard. And, that's a nice dynamical system, experimentally accessible. Why did I mention this? Because in that case, you have a frequency and it's natural to strobe your atoms. Like in a disco, there's a one sharp frequency. Why does everybody put all the systems to make them into first order systems? Well, what's criminal about it, it's subtle, because when you look at the original equation, it might have some beautiful symmetries which enable you to solve it. When you write it as a set of equations marching forward in time, so typical thing that happens in mechanics doesn't know the future from the past. Its equation is the same if I reverse the time. But if you write it in this form, the future looks like you psychologically feel it's very special, and past is different. It's things that already happened. So often you, by losing this intrinsic structure of the original problem, where you had some intuition, you find us as in this sausage factory where, everybody, all the meat is put in the same grinder and comes out of a grinder in the same way. And then you suddenly discover, and that will be, what's wrong, the second part of this course when you get to chaos, it actually doesn't make sense to do this, because you cannot predict the future if you have turned unstable, turbulent, chaotic systems into just marching in times. You have to think deeper. And that's, that's what this figure is that I'll return to several times today. Thinking how we think, it starts with Laplace and Lagrange, but it's still important today. There are other ways to solve the system. But in this course, most systems will look like this. Most of them be 1 or 2 dimensional, rarely 3 dimensional, with exception of Rosler simulation. And this marching in forward will look like it's working. And sometimes, kind of problems that Strogatz likes, it does work. It's this one-dimensional problems. So this is, again, show my picture. This looks like this is the law. It's either Newton or somebody has given you the law. And it has something that you don't realize immediately, but starts plaguing you seriously very quickly. It's not enough to have the law, because the law says, I'm sitting infinitesimally close to some state. And what the law is, if I change a little bit in time, how do I have to change in space to preserve the number of particles? Some, very fundamental thing. But it's differential and it's local. Now, I might be totally blind. To me, the world can look flat. It's a flat physics because I just look at first derivative. So that's a plane. And that's what the law seems to be saying. But then as I run around, I might get close to the edge of the whole thing, or I might have to adjust things at the edges, and that's called boundary conditions. So, the things not only have to be locally obedient and well-behaved citizens of an authoritarian structure, but the whole thing has to make sense. All of them have to fit in this box, for example, in a pipe or some kind of container that you use in your experiments. And that is global information. So very soon you realize you have to make sure that your global demands are implementable, or as we call, admissible. So it's not at all obvious, given a differential equation and given the constraints you would like to satisfy, it's possible. There could be no solution to this equation. It's nice to write it, but it could be great. So that's the first thing you have to realize. It's not just the equation. We would like to say, okay, we have initial value. And we would like to go someplace. But we also have to satisfy boundary conditions. And if you have taken a quantum mechanics course, you'll realize even the problem linear doesn't have to be nonlinear. This idea that you have Schrödinger equation, which is nice, simple thing that sits any place locally, is good. Tuk, tuk, tuk. But that thing has to fit into your shoebox. And when you're very lucky, that's what happens in quantum mechanics. It turns out boundary conditions can be met, but only for very special values of energies. And that's called eigenvalues or eigenstates. And the way you think of it, you really have this equation which describes oscillations. Second order equations typically have sines and cosines as their solutions. And you find out that only if the thing just vibrates in a very special way, which are the modes or nodes of a drum or a plate or a sapphire ball or something, boundary conditions allow you to have a solution. So that's most quantum mechanics of bound states and quantum field theory of finding masses of particles exploits this fact. So boundary conditions are immensely important. So it's just not just integrate, but it has to, you have to integrate in such a way that that it's consistent globally and not just locally. So that's the first thing you learn. You try to go local, but the world reins you in. You might say my state is something and try to compute it, and it might not be possible to solve the problem. That's the first thing you have to use. So we will ignore that in initial value problems. It'll turn out that boundary conditions mostly won't bother us very much. But if you need to drum or to play musical instruments, that's called two-point boundary conditions. And that says that, I can start out doing something in some directions, and I can demand when I'm done to do something else. So this is what happens when you drop a stone in the surface of water and wave goes out. And what you get here is only something that's compatible with what you get there. And you discover there are clever ways of dealing with it in which you vary some variables here and some there. They're not necessarily 2 points, but you divide the dimension of your space into boundary conditions on beginning and the end. And then you discover, this formulation is smart, this is stupid. So that's why I was complaining about it. So this is easy in this course, but often wrong. It's not a way how to solve problems. This one is difficult. Often encountered, highly non-trivial. Mostly we don't know whether it's possible to respect local law under given boundary conditions, and proving existence of the solutions and uniqueness, etc., is a big deal. So what we often have to do is, we actually have to do this numerically. Numerically means we can only do finite number of computations to finite precisions. And the way we do this is we go global. So, think globally, act locally. That's the whole thing. And how do we act locally? Well, we say, the best we can do is we can discretize. On n points. So the best we can do, we can say, we have time and space, maybe 3 dimensions of space, 1 of time, and some other symmetry of the problem that might be another coordinate, etc. So this could be lots of coordinates. And we say, well, the best we can do is we can divide this in discrete number of points and evaluate the value of the field. So this is field at position n and time t. And from them, put together an array, which is a homologous vector, if you wish, depending how you list it. Or today we like to say these are tensorial representations. And it could be that I have an instruction set that says, this is maybe a boundary condition or maybe some other set of instruction that says, or, in electromagnetism, this could be source of a charge field and stuff like that. So we call them sources. There's an instruction set, which also I have to specify over my spacetime. And this is not good enough as discretization because usually in good problems, like I'm looking at 2 quarks trying to scatter off each other, the space and time is definitely infinite, right? We're used to the idea that it used to be infinite before us and it's infinite after us. And maybe if we do some cosmology a la Roger Penrose, we might make it cyclic, but nothing on the laboratory scale of seconds. We're talking about, mega Googles of seconds when we think of these things. So that's irrelevant for our purposes right now. But we can put it in computer even when it's discretized. So the best we can do is we can truncate this thing and have a number of points. The moment we do this, our original equation, which was derivative on continuum, is now a set of points, and each one is an ordinary differential equation, but there are lots of them. So all problems of space-time discretization can be written as ordinary differential equations in time, in the spirit. And that's one way we do this. So lots of engineering deals with designing rockets or designing pipes or designing, plumbing or cars or bicycles or whatever moving in the air in this discretization way. So that's one way you can do it. Now, when we do this in 1 dimension and just in time, discretize in time, we'll immediately learn, the way this is written, this is very crude and might not work at all. That's called Euler representation, when you take just constant values on a set of discrete points. And we learned that actually it might pay off to. So we always have to discretize. There is no way to avoid it today. The least we can do, which we're doing right now, is discretize time, but we also have to discretize space-time. So there's just no way of avoiding this. That's the fundamental fact of our lives. And one obvious thing is you construct some mesh, or you buy expensive software if you work for a car company, I don't want to think, or you can call it a grid. or you can call it a lattice. So that's the crudest idea. The space that looks continuous to us can profitably be approximated by points. And if I look far enough, so the phenomena I care about span many points, it looks continuous to me. So that's how we write all physics, because we do not know whether space-time is discrete or continuous, but so far it looks continuous. The second idea is something that became clear to engineer Fourier, who was trying to make better steam engines, which was a big deal in 19th century. You can use something that we call today spectral, so not a very helpful word, methods. But you realize maybe if I'm looking at stuff that's smooth, so, you give me a megapixel image of your beloved. Now, if I blow it up by factor 1,000, I'll see something rather ugly. There'll be some pixelated random thing, nothing beautiful about it. But we both know that we like the general gentle shapes. So that is obtained by saying, don't look at pixels, which are like bar graphs with some stuff, but look at the envelope, smooth envelope, because that's what we really care about. And write this function you're interested in as sum of smooth shapes. So these are some continuous functions which you define mathematically with arbitrary precision. The simplest example is Fourier, but it could be lots of other kinds of things. So that's a functional basis. It's nice. The problem is if I get this pixelated image and it's megapixel, I need lots of them. And if I have arbitrarily small pixels, I actually need, let's say, minus infinity to plus infinity of these functions. So that's not nice, but then you realize, the function looks like a comb. It's actually not what I care about. It's called filtering or truncation. So you say, let me just look at finite number of these guys. That's called truncation. It has many other words. And, low pass filter, band filter, whatever you want to call it, depending what your job is, day job is. But basically, it says, look at your problem, and maybe before you discretize it, go to a sensible representation of it. It's given to you as a megapixel on a square grid, but actually the sensible representation is a discrete Fourier transform or a megapixel or something in terms of Bessel functions or whatever special functions there are, of which you understand how to manipulate them, what's orthogonality and other properties, regardless of how finely I can compute them. In that new basis, I just have to compute these coefficients. And it turns out that if I do that to my pixelated image, it's much more efficient. So that's the idea of spectral methods. You look at your problem, you have to discretize it, but Euclidean coordinates are maybe not the right thing, because if you can represent it as much more compact way, like it's 200 frequency and not a megapixel of pictures. And if you know how to go back and here, you'll give me, and that's what JPEGs are, you'll give me a JPEG that human will think it's the same figure, even though the number of bits needed to specify 6 orders of magnitude smaller than the original image. So that's one thing you should always do. Now I want to tell you, what's the danger of the obvious thing. Often if you have a very complicated shape and you're trying to find its eigenmodes, you're trying to make a drum whose perimeter is not a circle, but letter T for Georgia Tech or something, then there are no nice function of this kind that cover it up. If you have nasty boundary conditions, you might not be able to avoid this. So then you live with it, but you have to be aware of the following thing. The basic following thing is that whenever something has somebody's name, he most likely he or she did not do it. Or if he did, it was something totally trivial, not compared to what he really did. In this particular case, the man is a Swiss foreign worker working in Russia as a paid scientist at Catherine the Great's Academy of Sciences, because at that time, the autocrats thought that science was something that legitimizes their regime. So they hired, people like Euler to do the dirty work. And they did amazing work because, thanks to them, Russia has had amazing mathematics for centuries, but that was a way to import it. So Euler did amazing things, but here is what we say is Euler methods, which would be embarrassing because, of course, he did much better than this. So Euler's method says, I'm here, and someplace on the side, I imagine I have a little map which says, I am in Macon, Georgia, at M, and there is a highway that might take me to Atlanta, but it might take me to Banana Land if I take it the wrong way. And my map tells me how this highway goes and what's allowed velocity, and that's called f of x. This is this vector field. So we have this picture like that every place. And what Euler method says is, well, close your eye for a second, look at your device or something while you're driving, and just go straight. So there is a unit of time called time step. But because we've decided to call time x, it says that if I go unit of time at this velocity, I have to multiply the time by velocity to find out how far I got. This happens at an instant where my eyes were open or on the road, and so this is time, and this is my position in this one-dimensional world. And this whole thing is velocity. But now it's becoming this abstract notion of velocity that if I have a state space, I can strobe it at short periods of time, and I'll get these little intervals which are long if I'm moving fast and very short if I'm slow. The velocities. And in this way, I will get an approximation to where I'm actually time and later, because actually I'll be slightly different. And the error, it turns out, I'll make it is proportional to this time step. So that's called a first order method. And it says at time n+1, I'm here. So it says I have a trajectory. I'm going down, Interstate 80 or something. And at every instant, I'm provided the direction and velocity I'm allowed to do. But I go for a while pretending velocity is constant, and I make an error. So this is my error. But I say, so what's the big deal? If this is getting me off the road, let me correct my trajectory more often. And you can do this, but it turns out, this method does not cure COVID. And Euler would be shocked that his name is stuck to this. This is such a childish, silly way of integrating that nobody does it. So this is only done for pedagogical reasons. I'm here at position Y, and I end up at Euler's 1+1. Poor Euler. And if you put it on your stupid phone, it will either create big errors or be very slow because you'll have to evaluate this velocity very often, and that can cost money. So I'm sure Euler himself, who was amazingly good in integrating, he was, for example, amazingly good at estimating the value of pi, the number, which is, I forget, 7/3 in Tennessee or Kentucky, but Euler already had it to hundreds of digits. And Gauss, Riemann had even more amazing things. And the idea is the next idea, which right now it's called midpoint. And midpoint method says, don't just compute, but think. Even though thinking is extra cost, we all know that. More precisely. If you use Euler, you get an estimate for where you are after one step. Call this number K1, and it was given to you by Euler. Then you say, but it doesn't cost me so much to step half interval. So this is just a little bit more work, roughly speaking, doubling work, but reward will be great. So now this X is time and H is time. So I just go half of my usual interval. I can do this because I'm given, my velocity is given to me by Newton. It's a function I know for every time and every position. And now I use the guess that I had before, but just use half of it. So that's midpoint. That's why it's called midpoint. And I multiply this by h as well. Remember, h is time, this is velocity, so h multiplied, this is distance. So these are some kind of distances, k2. And now I have a new formula, which I'll draw you a picture if this doesn't make sense to you. that says, I start where I started. But then I use this improved guess, the midpoint guess. And then I estimate how big is my error. And it turns out this is got to time interval to the cube. So it says that if you're clever, you can improve your integral. So the price is you compute more points. In this case, 2 points rather than 1. By point, I mean compute velocity at 2 states of the system. But you're rewarded by decreasing the error as order of this time step. You know, you care about a couple hours it takes you to get to Atlanta, but these time steps are seconds because you have to do this rather often. So h is the ratio of these 2 times, the global time you care about in your integration step time. And you find out that you can make the error be small number times, I don't know, m. Where in this case, m is 2, but when you get smarter, m is 3, 4, 5. So this is the fundamental idea of improving integration if you don't know anything about a system. So you haven't thought, you're given your system, it's some stupid equations, you don't understand them. So I'd like to produce a picture to see what do they do, because one big point we learned from Poincaré is that you can be given equations which mean nothing. You can be given equations that mean absolutely nothing, because almost always the way, it's not just you that you're being stupid when you're taking a course. Nobody understands the consequences of differential equation. Nobody understands what it means that I write a bunch of differentials divided by it, and I write terms which are allowed by the symmetry of problem. We can do it, it's beautiful, but you have no idea what the consequences of this. We learned this from Newton. He could do Keplerian ellipse, and that was it. He couldn't explain the motion of the moon. It's a thing that was killing him most of his life when he was not killing other people as a sadistic head of British Royal Mint, or attacking other people that he stole ideas from or competed with. But he could never do this problem. He could just never do it. And Euler, released us from it. And he was so smart, he could visualize what global qualitative behavioral equation is, even though he wouldn't draw a picture for it, because it would mean he would have to pay extra money to the printer to create a plate for it. So there are no pictures, but he had them in his head. He describes them. He said, the picture is so complex, I will not attempt to draw it, and he doesn't draw it, but you will draw it in this course like nothing. Today it's totally simple. So if you don't know anything, you'd use this method. So there is a variant that everybody uses. So to understand what is due, I will draw a little picture. I've given you a link to Numerical Recipes. It's a very, very nice book that, it's from the 80s, but it's very useful today for kind of things you want to do. It's an intelligent, it is written by people who had to do real numerical computations because they care about general relativity and things like that. And there you have to think very carefully what you're computing. So here is what this means pictorially. So if I have my midpoint method, I've written some stupid formula for it, but what does it mean? So Poincaré says, well, look at it. I mean, of course, nobody understands formulas. And really, truly, I can quote Stephen Smale, the great mathematician, Martin Gutzwiller, the great, they will all admit they don't understand formulas. Now, maybe some people do, but, they're English priests or something. I don't know who they are. So we are computing a function, state of system, which for some reason we call y, as a function of time, which for some reason we call x. And what do this formula mean? So the first formula says, if I was very good, I would know, and often in these baby problems, I actually had no analytic solutions. So I would know that integral value of my state as a function of position as I start at initial point x0 and I go interval in time h that I call 1. Euler says, sorry, no, I drew it in a way that is not very impressive, but it says, if I look at the tangent here, I get a prediction. And I accuse Euler of being a klutz, that klutz Euler. But if I use midpoint method, what I do is I say, well, I know the tangent here, but that might be very wrong. So let me go midpoint way to h/2, evaluate the tangent again. So here it is, tangent on the midpoint. Now, what's the tangent? This function f is the tangent. It has dimensions of height divided by time. So this is what this tangent is. And this guy is pointing this way. And now what this method says, go to the midpoint and use that slope at the midpoint. That's what K2 is. So what it means is you actually increase by the slope, which has been improved by doing this calculation here. And you get a prediction, which is called a midpoint prediction. Much better than Euler. Now the true result is here. Yes?
Is the blue curve the analytical solution?
Yeah, the blue curve is usually infinite patience solution, because when you're, preparing your paper for publication, parts of it you can double the resolution and let the computer run 2 days instead of half a day. So usually you just get the better numerical thing, or you use a better numerical method, and then you compare it with Euler. And Euler is here, midpoint is there, and the difference is you use more information.
So the y coordinate of the dot with an x coordinate of h/2.
Yes.
Would be off the curve.
Yes. So that's what we are using here to compute K2.
Okay.
And then we stick K2, not K1. We stick that guy in, but this guy depends on K1 because we use the initial guess here for the function. So we compute yn, but we, move it to midpoint. Then we compute the slope at the midpoint and we feed that in. And that's what you are doing geometrically, but then you have to do a problem set to show you that if you're expanding the true solution as a Taylor series in powers of h, in this thing as a function of variable time step, you will find out that the first term that survives is of order h cubed, if you do this calculation. Whereas for Euler, the step was of size h, the error is size h squared. Now, when these are small numbers, this is a big deal, getting extra power of a small part, because things get smaller. So now, this is a whole school of thinking. So these things are called Runge-Kutta methods. And I suggest, there's a great temptation to just use software as given today because Python, Julia, MATLAB, everybody has libraries of things that various integrators. And they're black box, and if you're doing psychology, you just use this black box and publish. But from a physicist or applied mathematician, I expect much more. I expect that you understand why you're using particular integration. So Runge-Kutta, which is the generalization of what I just told you. So Runge, names of two people in Germany in 19th century, or maybe beginning of 20th, I forget. Again, Runge has done serious stuff, but we're only celebrating for the childish thing attached to the name, and I can't remember what Kutta did. Say, well, okay, so I get it. What I'm supposed to do, few measurements on my curve. So I'm supposed to evaluate the velocity at few points and then adjust these coefficients in such a way that the Taylor series starts at h1 plus m term. And you can do that, you get a hang of it. So I'll just tell you how Runge-Kutta does it. Fourth order, that's a standard thing. And I suggest you program it just and think about it and test it. And then use, some beautiful integrator your software provides. So they say, well, the way this works, we started with Euler. Then we went to Midpoint and improved it. So, when I looked at the slope or the value of the function, I used that to start evaluating my velocity again. That's called midpoint. But then, can I add a new evaluation? So now I'm still at time. And if I made some errors here, I say, well, why did I just go to half point? Why don't I also evaluate what happened after full interval? Wouldn't that be better? So I started at time n, xn. I measured what happened at half of the interval, but why not measure also what happens at the end? So that's what this evaluation is. And, I reuse what I know from midpoint. So that's another evaluation. And now I get a good guess for my thing that depends on the previous ones. So now I evaluate at the end again. but I reused the, improved midpoint. And now I piece those things together in such a way that I expand everybody's Taylor series. Things cancel up to order 4. So that's why it's called fourth order. And there's kind of some cute algebra you do. I've done it as an undergraduate. Every undergraduate should do it. I haven't done it since, but can be a problem. So you put all this stuff together and you find out something that's good to H5. And what does this mean in practice? If I'm being silly and I use Euler, which you never should do, Euler never did it himself, then I might have to use seconds to drive from Macon to Georgia, to Atlanta. But if I use the 3, what you're essentially computing more and more terms in Taylor expansion, even though you're going in just the first order derivatives, you're using the first 3 derivatives to do this. And, maybe I have to give a correction, not in seconds, but every 5 minutes. And it becomes a very big deal when you're trying to solve exoplanet system. You have a solar system like ours, but planets have different masses, different distances, and you're trying to figure out, how that behaves, what are typical periods, etc. It really pays off to continue with these methods and do calculations. And people who did this, they had to do very precise astronomy, celestial mechanics in 19th century and early 20th century first half before advance of computers. And they did it. They have some fancy name, secular method, etc. But this is the spirit of it. Can I use more and more local information to propel me further and further in reliable computation? So what this particular method says is, if there's a true answer, so I start here, and here is the truth to 64 digits. I approximate it by doing one evaluation at this point. Then I do an evaluation in mid-interval. And I compute this mid-interval slope this way and then that way. So these are done on mid-interval, but I'm using preceding one to improve the estimate of the slope. So I get 2 of these guys, 2 and 3. And then I finally nail it by going to the end of interval using, the best slope I can do, kind of best curvature, and that gives me the 0.4. And the truth is, rather close to what I wanted. So this is what you do if you're total ignoramus and you don't understand what you're doing. This is the best job you can do. So this is a decent integrator. And I strongly suggest you do it. I strongly suggest you write the program and understand everything, how it works. Or maybe write a more complicated integrator, than this one, but just try to understand one of them. So now what's wrong with this? We will continue next week. I'll tell you the truth next. Please come back in a week because everything will be revealed.